The forces that hold the atoms of a molecule or a compound together are called chemical bonds. The likelihood that an atom will form a chemical bond with another atom depends on the number of electrons in its outermost shell, what we call the valence shell. An atom with a valence shell holding 8 electrons is chemically stable, which means it's not likely to form chemical bonds with other atoms. Neon, for example, has 8 electrons in its valence shell, and for this reason it doesn't bond easily with other atoms. The valence shell of hydrogen and helium is the first shell. The first shell, remember, only holds 2 electrons. Because of this, helium has 2 valence electrons, so it's stable and it seldom bonds with other atoms. Hydrogen, on the other hand, only has 1 valence electron, so it readily bonds with other atoms. The atoms of most biologically important elements don't have 8 valence electrons. So under the right conditions, 2 or more atoms can interact in a way and produce a chemically stable arrangement of 8 valence electrons for each atom. This principle, called the Octet Rule that I mentioned earlier, helps to explain why atoms interact in predictable ways. One atom is more likely to interact with another atom if doing so will leave them both with 8 valence electrons. For this to happen, an atom either empties its partially filled valence shell, fills it with donated electrons, or shares electrons with other atoms. The way that valence electrons are distributed determines what type of chemical bond will result. So we're going to talk about 3 different types of chemical bonds. Now, when an atom loses or gains an electron, remember, it becomes an ion, so it has a charge. If an atom loses an electron, then it has lost one positive or one negative charge, and therefore it has one more proton than it does electrons, so it becomes a positively charged ion that we call a cation. So if you remember the T in cation as a positive charge or a plus sign, then you can remember that cations are positively charged. If an atom gains an electron, then it has one more electron than it does protons. Remember, electrons have a negative charge, so negatively charged anions have gained an electron, and they are called anions. So remember the N for negative sign. So the negatively charged ions gained an electron and have a negative charge. So these are some more of the common ions that are found in the body, and you'll see these throughout your studies. So let's look at some ways that these bonds are formed. So when atoms gain or lose one or more valence electrons, ions are formed. Positive and negatively charged ions are attracted to each other. Opposites attract. The force of that attraction holds the ions together, and that is called an ionic bond. So let's look at sodium and chlorine atoms, the components of just common table salt. Sodium has 1 valence electron, so if sodium loses this electron, it's left with 8 electrons in its second shell, which then becomes the valence shell. So as a result of losing that 1 electron, the total number of protons, 11, now exceeds the number of electrons, 10. So the sodium atom has become a cation and is positively charged. So when we write that, we write Na, the chemical symbol for sodium, with a plus sign. If chlorine gains an electron, then it will have a complete octet in its third electron shell, which is its valence shell. After gaining an electron, the total number of electrons, 18, exceeds the number of protons, 17, so the chlorine ion then becomes an anion, or a negatively charged ion. So when we write that, the chloride ion, we write Cl with a negative sign. So the resulting positive and negative charges on the sodium and the chloride pull those ions tightly together and form an ionic bond. Most ionic bonds exist as solids and repeat themselves in crystalline form, so most of them are salt-like structures. An ionic compound that breaks apart into positive and negatively charged ions in solution is called an electrolyte. Most ions in the body are dissolved in body fluids as electrolytes, and they're named that because they are able to conduct an electric charge. A covalent bond forms when two or more atoms share electrons rather than gaining or losing them. Atoms form covalently bonded molecules by sometimes sharing 1, 2, or 3 pair of valence electrons. And that should be on that slide. So here you can see examples of that where you've got two hydrogen ions sharing 2 electrons. So remember, hydrogen only has the 1 electron shell and it's full with 2. So by sharing electrons, both of these hydrogen atoms are fully filled and absolutely happy. So they form a hydrogen molecule. With oxygen, you see 1, 2, 3, 4, 5, 6 valence electrons in each oxygen atom. So if they both share 2 electrons, then both atoms have a full valence shell with 1, 2, 3, 4, 5, 6, 7, 8 electrons. So that is a stable molecule. And the same thing with nitrogen, which is an example of sharing 3 valence electrons. Covalent bonds are the most common chemical bonds formed in the body, and compounds that result in them form a lot of our body structures as well. So these are sharing equally. You can have covalent bonds where they are not shared equally. The electrons are not shared equally. If they do share the bonds equally, which simply means that one atom doesn't attract the shared electrons more strongly than the other atom, which is what we saw on the previous slide, then that's called a nonpolar covalent bond. Looking at these two, where we have the carbon and the hydrogen and the oxygen and the hydrogen, we have what's known as polar covalent bond. So the sharing of the electrons is unequal. The nucleus of one atom attracts the shared electrons more strongly than the nucleus of the other atom. When polar covalent bonds form, the resulting molecule has a partial negative charge near the atom that attracts the electrons more strongly. This atom is said to have a greater electronegativity and attracts the electrons more to itself. A very important example of a polar covalent bond in living systems is the bond that forms water, so the bond between the hydrogen and the oxygen, forming the molecule of water. The nucleus of the oxygen atom attracts the electrons more strongly than the nuclei of the hydrogen atoms. So the oxygen atom is said to be more electronegative. Polar covalent bonds of water allow it to dissolve a lot of molecules that are important to life. The bonds between nitrogen and hydrogen and those between oxygen and carbon are also polar covalent bonds. We'll talk more about the importance of water and the polarity of that later in this particular discussion as well. And then finally we have hydrogen bonds, which is our third and weakest type of bond. So a hydrogen bond forms when a hydrogen atom with a partial positive charge attracts the partial negative charge of neighboring electronegative atoms. Most of the time it's usually going to be a larger oxygen or nitrogen atom. So when this happens, the hydrogen bond results from attraction of the oppositely charged part of the molecule rather than the sharing of the electron as in covalent bonds, or losing or gaining electrons as in the ionic bonds. So hydrogen bonds are weak and very easily broken, and you'll often see them represented by dotted lines. The hydrogen bonds that link neighboring water molecules together gives the water a tendency to have cohesion or the ability to stay together. The cohesion of water molecules creates a very high surface tension. That simply is a measure of the difficulty of stretching or breaking the surface of a liquid. The boundary between water and air, the water surface tension is really high because the water molecules are much more attracted to each other than they are the molecules in the air. You can see this when a little spider walks on water or a leaf floats on water. The water surface stays together rather than coming up and getting all around the spider legs or the leaves. The influence of water surface tension on the body can be seen in the way that it works for what is needed for breathing. A thin film of watery fluid coats the air sacs of the lungs called alveoli. So each time we inhale, we have to have enough force to overcome the opposing effect of that surface tension so that the air sacs stretch and enlarge when we take air in. And again, even though hydrogen bonds are very weak, very large molecules such as DNA contain thousands of these bonds. When they all act collectively, hydrogen bonds provide considerable strength and stability and can help determine the shape of large molecules that are very important in the human body.